Yep. Hi. Nice to meet you.
Great. Hi.
I,
Hi.
I
Nice to
look
meet you.
after the facility in Thailand, and I guess if we go on to the next phase where we actually, where you actually engage us for a project, then all your experiments will be taking place in our lab here in Thailand.
Okay. Interesting.
So we were just saying that we have a GMP facility as well in Thailand. So if it would warrant it, the project would go well at the R&D level, then we could easily and effortlessly move into our GMP suite there to produce clinical grade encapsulated cells.
And right now, as I understood, you're discussing the size of the encapsulation. I just heard Carlos speaking about a small box, and then you said something about 0.7 millimeters. This is the size of the encapsulated cell, right?
Yes. Between 0.6 and 0.7 is usually the range of our like standard encapsulation process.
And at the
And
research
for me,
level,
interesting.
we've been down to about 0.2, but it's, yeah, so it is possible, but of course then you have a lot less cells and more material relatively.
But sometimes it's for us it's also interesting to work in this and maybe in this small sizes. Maybe there are not a lot of cells in, but then maybe the amount of encapsulated cells will make the importance then during the treatment, because we like to use the cells also for intravenous application. And maybe this is also an interesting point. We like to do some experiments also. So this might be then the more experimental stage, how this might work then in first of all, of course, in animals, or if this is causing some problems, or if this is then a great difference than using the cells without encapsulation, so the non-encapsulated cells. You have already some experience with that in animal models?
Let me think. Most of our animal model work has been done with 0.5, 0.6, 0.7 size capsules. Also the human clinical trials were done that way, and they were delivered also to the bloodstream, but it was super-selective catheterization, which allows you to place quite precisely the capsules where you need them. And in that case, it was the blood vessels leading to the pancreas, because it was a trial for using pancreas cancer. We used the same capsules though in a clinical trial in dogs where they had spontaneously occurring breast cancer, and there the capsules were injected around the tumor into the skin.
Locally.
Locally, yeah.
Yes,
We've delivered capsules to IP as well, intramuscular, in animal models. There's many sites that you could possibly choose.
You got already experiences in articulations with the encapsulated cells, because sometimes the material is causing maybe some problems intra-articular, because there's a if you add certain material into the articulation, of course, it could cause damage with the cartilage. So you have also there some experiences?
No, we've not so far, but we have a full tox. So this is considered a device by the regulator. So we have a full tox study on the ICH, different tests that are needed for medical devices, and it's negative in everything. It's also non-immune and non-mutagenic, like in Ames tests. It's a non-skin irritant. It's been in patients for up to 2 years in that study where they were delivered through the super selective catheterization.
And the long life of this capsules, so how long they resist, let's say, inside the body?
Right, so in those patients, they were there for 2 years, but we couldn't actually retrieve them afterwards. But in animal models, we've been out to about 6 months. In the dog trial, for example, we could retrieve the capsules, and they were fully intact and the cells were still alive.
After 6 months?
Yeah.
Wow.
We've also had porcine islets in diabetic rats, and we've retrieved those after, I think it was 5 months. The capsules were still alive. The cells as capsules were still intact. The cells in the capsule were still alive. They were still making insulin, and that was an immunocompetent rat. So it seems to be an effective immunoprotective device.
You also is there also publications so to read something about that, because if this is what I'm thinking, if maybe there's encapsulated cells are maybe longer, still stable after 5 months, could cause some problem because of a kind of hyperproliferation phase of the cells, or they are proliferating, or they are in a steady state situation inside the capsule.
They're in a steady state situation. These are cells that we've tested so far. We've had HEC-293 cells, which is actually an immortalized cell, but even though it's immortalized, it stops growing. It sort of reaches a 3-dimensional conference. But we've done hybridomas as well. Again, they're tumorigenic, but they never got out of the capsules. They stopped growing.
Okay.
We've done stem cells. We're doing quite a few different cell lines.
And the design of the capsules, they have...
The only one we wouldn't work with is CHO cells. They seem to be quite aggressively dividing, but also anyway, CHO cells produce endogenous retroviruses, so we wouldn't want to go into patients with those.
And the capsules, they have a liquid core and a hard, or
Your internet connection, Chris.
if it's like a hydrogel, and maybe your design, the cells cannot. Sorry, you cannot hear me? Oh.
Yeah, we missed that.
Yeah, you're back now. Can you repeat the question, please?
Yeah. So the question is, so the design of the capsules might be like that the core is maybe liquid, and the borders are quite, let's say, they are not semi-permeable, I think, for the cells. So they are really tough encapsulated, so they cannot leave maybe the capsule. But for example, if you use, let's say, a normal hydrogel and a capsule with maybe only one phase, I think it's designed like that the cells, they can leave the capsule. But I think your design is more like that only maybe the produced proteins from the cells, they can leave maybe the encapsulated, because otherwise, yeah, of course, if you use this HEC cells, then you could, after 5 months, you could end up with big problems in the animals.
Yes. No, it's exactly like that. We've also done a study, it's been published, I think, as well. I know it has been published with a stem cell company actually using encapsulated menstrual stem cells to produce exosomes. And it acts as a semi-permeable filter, so a semi-selective filter, so it allows the exosomes out in a purified state. So the stem cell group that we work with characterized the exosomes and compared them to classically purified exosomes, and so they were much purer, really, that came out of the capsules. So yeah, you're right, what you say. I mean, we do have ideas, if you want to release the cells, that we could maybe modify or co-encapsulate with cells that can have an inducible cellulase. That's the only way that would, release the capsule, release the cells from the capsules. We know we can add cellulase from outside of the capsule, and it will dissolve and it will release cells. But yeah, the whole thing's being designed actually to be a long-term implant and not to release the cells.
Yeah, so when we make the capsules, we basically mix the cells with cellulose sulfate, and then we have a machine that creates single drops, and then they drop into a bath of a second chemical, and that reaction then kind of like encloses the cells inside, and then basically you get a nice round 3D sphere with like a small amount of cells inside to begin with, and then we culture to have the cells grow inside to eventually fill up the capsules. And from like testing we've done in the lab, like the capsules themselves are quite elastic, so you can push down on them and then they can bounce back into shape. So they're very, very robust yet elastic. Yeah.
Yeah. Yeah. Yeah.
I think this is super interesting indeed, yeah. Um, I don't know if it take that long to use this encapsulated, yeah, but we can discuss that because I think it's if the material is already tested and also in vivo, not only in vitro, then it should not be the biggest problem because we already use this biospheres, of course, non-encapsulated. And it really might be super interesting. Even could think about a therapy with both possibilities at the same time. So then, because if you add this really encapsulated cells and the cells cannot leave the stuff, then you could use them for chronic problems. not only talking about the lung, also talking about tendinitis or whatever. So if the cells, they really then survive 4 or 5 or 6 months and they cannot move away, and you have this tiny bioreactor close to an inflamed tendon or whatever, this sounds very, very interesting to me, because this is a long-term treatment. And if the cells, if they stay active, this is also the interesting thing to see if the cells are staying active in this encapsulations, because they need, I think, a permanent support with to keep the metabolism ongoing. And if if the capsules are able also to intake, um, let's say, body-owned proteins or substances for the cells, this is super interesting, really, I must say, yeah.
Yeah. I mean, yeah, it sounds like an ideal use for the capsules. I mean, and as you're saying, I mean, it's like a two-way street. So it's whatever the cells encapsulated produce,
Mm.
but they are influenced by being in the body. So, for example, in those studies with the diabetic rats, I mean, the capsules were really responding, and they were really encapsulated islets, so maybe it's no big surprise. But they were really responding to, blood sugar. So when the blood sugar went up, more insulin came out.
Yeah.
The blood sugar went down, the amount of so it really sort of replicated the normal system of islet cells controlling blood sugar. And
But
that
I think concerning diabetes, sorry.
Sorry, that went on for 5 months until they were explanted. And as I say, the capsules were still intact and the cells were still viable and producing insulin when they were recovered. Sorry, I interrupted.
Okay.
So, like,
Room temperature.
no, it has to be frozen. So like encapsulated HEG cells have been kept frozen at -80 for up to 5 years.
And descending in cooled or in ambiental situation is possible?
Mm.
I mean, we've had cells in cell culture for months, as long
Yeah.
as you keep changing the media. So I mean,
Yeah, I think if you want to keep it in room temperature or at 4 degrees, then it depends what we freeze it with. So it may have to be like a non-DMSO based medium, because otherwise that will become toxic for the cells.
Right, right.
but correct me if I'm wrong, Rahul, but when we have encapsulated some MSCs before, right? And did we ship those? I can't remember now.
Yes, we did. We froze them down in stem cell banker. So it's a freezing media that is specially designed to cryopreserve stem cells. But then those encapsulated cells then have to be kept frozen for long-term storage.
And
Yes. Yeah, so we have a thawing protocol that we can share with you. So yeah, it's like a few washes with DPBS, and then we typically thaw into like a highly concentrated media with serum just to help with the recovery, and then you change back to your regular culture media.
Which serum you're using? This is animal-derived serum, or you use then this human serum, or any specific
fetal
calf serum?
Yeah, fetal calf serum, yeah.
but
Okay.
approved for GMP.
It's like South American origin, so it's like free of all the prions.
Okay. Okay. South American.
Yes.
Free of prions? South American is free of prions, really? I thought Australian is free of prions. Okay. But Carlos and me, we heard also about a medium which can be used to send cells in room temperature or even under cooled conditions, and to keep them alive about 5, 6, 7 days, not only alive, but in a good stage. You heard about that, or are you using this kind of medium also? I think the supplier comes from China.
We've heard of a few because we did have one company reach out to us a few months ago where they wanted to do a stability study to maintain their cells at 4 degrees. So as part of that project, we were researching a few different preservants that you can use. There are a lot out there, but obviously we'll have to test them with your cells. Most of them are used to preserve tissue, but then they can also be used to preserve cells. But yeah,
Of course.
the maximum range you get is usually not more than a week.
And the viability then after 5 days, it's still 80-90%, or it's lower?
So they claim, but we've never tried it.
Okay, I
Yeah.
see.
Yeah.
Okay.
Yeah.
So what we've normally done is, I mean, obviously there's difficulties, logistic difficulties shipping cells, but we usually use a dry shipper. So you pre-fill it with liquid nitrogen, it's absorbed into the walls. So there's no actual physical liquid in there anymore. So it's safe, so to speak. The walls are soaked in the liquid nitrogen. Then we put the cells in that and ship it. And that's worked quite well for us, right, Ro?
Yeah, so that's worked well for sending cells. And then for the encapsulated cells, we usually just ship on dry ice, and that seems to be okay. Yeah.
And we've shipped to the US, to South America, because that's where that stem cell company was when we did the exosome release, to Japan, to Australia, and to Europe. So we have quite a lot of experience shipping stuff around. Very important stuff.
Interesting.
Ready.
Yeah.
Yeah. Yeah. Yeah.
Switzerland.
Yes, I think.
I mean, when we first started with this technology, I vaguely remember now that we did keep cells at I think 4 or 6 degrees, and had like how many weeks survival? I think 4 weeks or something like that. But that was with hex cells. I mean, the hex cells are a little bit more hardy, I guess, than MSCs. So it's something that would have to be tested anyway.
Yeah, I think as we develop like the details of the study, we can certainly add in a process where we maybe test a few different cryopreservants. That could be interesting. We do have a list of like 4 or 5 that we looked at for a different project, as I mentioned. So we can always buy those to test.
So what we wanted to start in our laboratories is to start with a normal hydrogel, not to use the really perfect round encapsulated cells, just to test in the very early stage something about the conditions of the hydrogels to keep the cells alive or in a pro-proliferative state. This could be maybe interesting just to check with a microscope, or then maybe try to get some supernatant from the gels and to test for the contents to see how far you can find proliferation factors, or if you release the cells from the gel, if the key 67 signal is still there, and this might be interesting for a certain start. My question might be if because we looked into the market to find some very basic hydrogels and to combine maybe 2 or 3 different compartments, if it might be possible maybe to do some experiments in our laboratories also, maybe in parallel to yours, and to compare the results. You might be open to maybe send us some samples to create some hydrogels in our laboratories, come in to have to try something, or you say, okay, if we design the stuff, this happens in our laboratories only.
An interesting one. I mean, we've combined our encapsulation technology with matrix proteins like laminin and things like that in the past, and we know that that works. But the problem is, I think, where we feel there could be problems. I mean, the kit basically works like that you had the solutions and then you pass them through a needle. But the disadvantage was the capsules were very large. They weren't homogeneous. And of course, that affects cell survival. I mean, once you get out beyond 0.7 millimeters diameter, then you start to get issues of hypoxia, cells dying in the capsules or whatever. So I don't know whether you have an encapsulation device or machine where you make your hydrogels in, or whether you make them in a different way.
Yes, sir. Yeah.
I mean, our encapsulation material, as I mentioned, is, can be made at GMP standard. We have made product for other companies testing for clinical trials. We have a drug master file with the US FDA. We've done all the tox testing that's required for hydrogels, medical devices in general. So all of that would be there in place. I think, as far as I know, I mean, I don't want to preempt Sigma or Merck or whatever, but I think that they don't like the risk of selling anything for clinical use, to be quite honest, because responsibility might fall back on them, and they're a bit nervous. Yeah.
I agree. Yeah. Yeah. And I think if you were to do like a proof of concept study with us, typically how it works, I don't know if Walter explained it to you in the first call, is that like you would send us the cells with like your culture protocol, like what media you use, and we can source that so that we do everything exactly the same as how you do it. And then we basically expand the cells to encapsulate, freeze them down into vials or syringes for you as per your requirement. And then we can do some basic assays here, like a decapsulation cell count to check on the viability. And then we basically just send all the vials back to you to do your own testing. And usually,
Okay. Mhm.
and usually that kind of study is like in the range of, I guess, like $15,000, something like that. Right, Brian? Like, yeah.
Yeah, it depends on how much you
Mhm.
want us to do and how much you want to do. But you touched on something important that maybe we didn't stress, Rahul. That is that we have a reagent that can make the capsule fall apart when it's in cell culture. So it doesn't work in vivo, but in cell culture, we can make the capsules sort of dissolve and release the cells. And the interesting thing about this is it's non-toxic for the cells themselves. So you can retrieve all of the cells out of the capsule and, test about whether it's affected expression of key markers or whatever. I mean, in our experience, it's never affected the cells at all. And we've looked at de-encapsulated hex cells, but we've looked at some stem cells. We had a publication about that.
Yeah. Yeah, because we did one project with another stem cell client where we were trying to optimize the growth of their stem cells. So like we tested 6 different stem cell media and then collected the media to send for FACS to check the properties of the stem cells. So like we can do basically any kind of in vitro testing that you would like us to do. And we might do it
Mhm.
ourselves, or if there's certain assays that we're not equipped to do ourselves, we have a network of suppliers we work with locally that we can outsource those tests to.
Mhm. Okay, this is interesting.
And so
And the
that,
idea of these proof of concept studies is not that we make huge amounts of money out of this. It's more like we just recoup our costs because obviously in the long term, we're interested in long-term partnerships um, to develop encapsulated cell technologies for
Mhm.
different uses.
and
So
it's
that's our aim, really.
it's usually very customized to the client's requirements as well. I mean, like the framework is pretty much the same. Like it's always expanding the cells, encapsulating and filling them down into
Mhm.
vials. But then all the tests you want done, how many capsules you need, how many cells per capsule, all of that we can kind of control.
Okay. Mhm.
There is a minimum run size though, right? So the minimum amount we would produce is how many roll in one run?
I mean, the smallest encapsulation we can do right now is with like 5 ml of SCS. So that would produce roughly 15 to 20,000 capsules.
Mhm. And the content of every capsule will be 4,000 cells, each capsule, or?
Yeah, with stem cells in the past, we've because they naturally grow quite slowly and are very difficult to culture, we don't normally manage to get a full capsule. So I think I'll have to go back and look at our data from the last stem cell client we had. But yeah, usually one capsule would contain a few thousand cells, like in the range of like 3 to 5,000, I think.
Although there are differences between different sources, I mean, origins of stem cells as well. So when we
Yeah.
did those vegetable stem cells, that was something we didn't do in Thailand, but we did in Singapore because that was a few years ago. And back in the day, we were doing encapsulation of cells in Singapore too. Now we're just doing bacteria there. But there we got better filling with those menstrual stem cells. So it varies from cell, and I guess it also varies depending on which media. I mean, even you saw that role, right, when you tested
Mhm.
those 6 different media.
Yeah. Right.
Yeah.
So from your culture experience of your cells, is it difficult to get around 10 to 20 million cells?
No, it's absolutely easy. Depends always from the cell number you start the cell culture with, but
Yeah.
10 to 20 millions you can get in a 3, 4 days. Yeah, or
Yeah.
everything depends from the cell number you start with, but
Okay.
normally we use this T75
Nice. Yeah.
bottles, yeah, and in a 3 days they are confluent, and each bottle contains then between it depends how dense and depends from the source of the stem cells, but up to 10 million cells. This is then of course 100% confluency in the bottles, but up to 10 millions and not longer than a week.
Perfect. Okay. Then there should be no problem because we
Yeah.
usually encapsulate between 2 to 4 million cells per ml of our
Hmm.
cellulose sulfate. So yeah, we would need anywhere in the range of 10 to 20 million cells for like the smallest encapsulation. So if it's not difficult to get that many cells, then like we could
No.
even start with just like one vial of cells from you that we would expand and we can take it from there. That would be like the
Hmm.
most simple setup.
And then we need to know which media you use, the growth conditions. I mean,
Yeah.
the simplest, the cheapest way forward would be that we do the encapsulation, we maybe do the viability testing, and then we send them back to you. But if you want us to do other studies, we're able to do other studies too.
Hmm. Was it might be
But to do that, though, we would need to know the media, because we need to cost the media, how much media would be needed, the growth of the cells. We need to know how many days.
Oh, this is not too much. This is absolutely in range. Yeah, yeah, it's not too much.
Yeah.
For us also might be interesting to know if um, you have different models of capsules. Yeah, so this means concerning material, if this is a soft capsule, if this is a hard capsule, is a liquid core capsule, so maybe there are 2 or 3 or 4 different standards you're offering, because this could be also interesting for us, of course, for the chronicle model and for maybe acute model where we want the cells maybe to disappear from the biospheres, from the encapsulated, from the
Yeah,
capsules. This would be also interesting.
that's an interesting point. That's something we can play with, because we can play with the gelation time, so we can make them more robust or less robust, and maybe
Yeah.
that alone is enough to address what
Mhm.
you're saying without doing any additional manipulation. So that would be maybe an easy starting point. And if it didn't
Mhm.
work, then of course we've got other ideas like the cellulase and whatever. Yeah.
Mhm.
So
Okay.
how should we proceed? Should we send you the sort of questions that we ask to be able to do the quote,
It
or
might
would
be
you like to?
perfect. Yeah.
Yeah. I mean, I think actually if you have like a culture protocol and you send us that, that should be enough to get us started on like at least a standard quote, and then we can take it from.
Mhm. Mhm. So yeah, we can send you this information. This is not a problem. And on the other hand, maybe you can send up the information because of the different qualities of the capsules. Yeah. And maybe how many cells each capsules are necessary so that we can make our yeah our calculations.
Funny times.
We need to send and in the cell culture over there, the standard prices. So this would be also interesting.
Yeah.
Yeah, so I'm very sorry for the connection, but it's quite bad. So just talking about a kind of standard prices, and yeah, just to get for us an idea um, about what amount of money we are talking, and we need to calculate with.
And of course, it will be an iterative process. I mean, it can be backwards and forwards if you have questions from us or we have
Yeah,
questions
yeah.
from you, until we get the final thing something where we all want
Okay.
it to be. Yeah. Okay,
Okay, perfect.
so it was great to meet you.
Yeah, like. Yes. Yes, I think we should all be copied in, but I can write my email in the chat now.
Yeah, Rahul is really the person for the nitty-gritty, I think.
That's Brian's, yeah.
I'll try and dig out, if you're interested, I'll try and dig out that paper about the exosomes, and maybe we have some data on stem cells as well. What I have to say is that not everything we do gets in the public domain, because sometimes it's like this, it's a collaboration, and a collaborative partner says, no, we don't want anyone else to know what we're doing. So we do have a lot of expertise and data that we can't share with you, but you would benefit from, because we know, like, we've worked with stem cells before or whatever. But some of the stuff is in the public domain, like I say, the exosome stuff and some early stem cell work, and I can send you those publications if you like.
Yeah.
Okay.
Yes,
Yeah.
have a good rest of the day. We'll be in touch.
Yeah. Great.
Looking forward to it.
Sounds like an exciting project, and yeah, nice to get to know you, and yeah, have a great day.
Oh, thank you.
Okay, bye-bye.
Thank you.
Bye.
Bye-bye.